great pleasure to introduce Mate Soos, a good friend, collaborator. So Mate obtained his PhD from India in 2009 and has since been working in both academia and industry on several things, including formal verification, breaking lightweight crypto primitives, and IT security. He is the author of the very widely used SAT solver, Crypto Mini SAT, and he has worked on model counters like approximc and Ganat, and also the uniform sampler, almost uniform sampler, CMS Gen, the probabilistic sampler Unigen. To his credit, he has helped reverse engineer and break several lightweight ciphers, and among others, through a combination of SAT solving, algebraic cryptanalysis, GPGPU, and FPGA programming. He is currently with Ethereum Foundation, working on formal methods tooling for Ethereum Foundation, and is also part-time affiliated with National University of Singapore. Okay, so Mate, floor is yours.
Thank you so much for the introduction. It was very kind of you. Yeah, so I am Mate Soos, and I'm here to talk about HEVM, a smart contract verification tool that I've been working on in the past 2 years at Ethereum Foundation. Supratik already did the rundown, so I'm not going to go too far into this. But one thing to note is that a lot of the things that I have done and we have done with Kuldeep is actually preprocessors and in-processors, in the sense that a lot of the work we have done with Ganak and approximc wouldn't have worked with in-processing and preprocessing. And a crypto mini SAT itself has a large array, a vast array, I would like to say, of in-processing primitives inside. And in some sense, when I went to HEVM, of course, I know how to hit a nail with a hammer, and I've built a few hammers. So I went to HEVM and I did what I used to do, which is to build another hammer. So it is in large part a rewrite system, HEVM, and I'll talk about it later. So first, I'm just going to do a bit of a recap of the sort of the basics of what is needed for me to be able to explain what HEVM is about. So I'll talk about testing Ethereum blockchain. As some of you know, Bitcoin, Ethereum may be a bit more novel, and I'll talk about symbolic execution, of course, and then I'll talk about HEVM in an overview and in more detail, and then I'll try to conclude. So first, testing. So testing is a discipline. It's not something that people write. I mean, people obviously do write tests in an ad hoc fashion, but when you do it properly in a serious way, then it is a discipline. And when it is looked at as a discipline, then typically people will talk about this testing pyramid, where you have the unit tests at the bottom, and then there's the module test, integration test, user acceptance test. A lot of people only write user acceptance tests, so that's kind of like the external way to use your tool, like, for example, the options that you give on the command line, or the API calls that you interact with the tools from the outside. And then at the top is what's called exploratory testing, which basically encompasses fast testing and manual testing and symbolic execution and all these kind of, I would say, more fancy systems that are not traditionally associated with testing. And when you write tests, you usually write 2 types of tests. Like, you write positive tests, which is what most programmers or engineers will write, which is that I expect this to do this when I send this API request, and then you hope that it sends back the response that you expected. This is what's called a positive test. A negative test is more rarely written, is when you for example, if I send the wrong password and username combination, it should not log me in. So that's not a positive test, because engineers will typically just write I send the correct username password combination, it should log me in. The negative would be the opposite, so I don't send the correct one, it should not log me in. And then there is, of course, what would be very nice to write, and some people do write, and if you work with SAT solvers, you write quite a lot, is invariant tests, which is they check that a certain invariant holds about the state of the system at all times. And that is very important, for example, if you write a rewrite system, because a rewrite system should never, for example, change something that is satisfiable into unsatisfiable, or something that is unsatisfiable into satisfiable. So an invariant there would be that if it was satisfiable and now I do this rewrite, it should still be satisfiable, and vice versa. Symbolic execution can help with all these three types of tests. There are other tools to do it, and I'll talk about that as well. But symbolic execution is a very powerful way of expressing these kind of positive, negative, and invariant tests, because it can be a generic description that you can write, and you can make it apply to all of your systems in one go. So it's supposed to be a really nice tool to do this. Of course, nothing comes for free, and we'll talk about that in a moment. So let's talk about Ethereum. So Ethereum is a blockchain, just like Bitcoin. For example, if you have heard about Bitcoin, the difference between Ethereum and Bitcoin is now rather large, but originally the difference was only, quote unquote, only that Ethereum could actually execute quite complicated code, in particular Turing complete. The Ethereum virtual machine is Turing complete, whereas the Bitcoin actually already does and still does execute some instructions, so it's not completely unprogrammable, but EVM is Turing complete. And so that means that it has its own VM, which they call EVM, so Ethereum virtual machine, which is a stack-based VM, and it has its own executor called the Geth, the Go Ethereum client. It has so-called contracts, which are basically what you would normally call classes or objects, actually, in this case. You program them as classes, and of course they get instantiated as an object, with their own storage, their own memory, their own call stack, just like a normal virtual machine you would expect. What's kind of interesting about it, it has ACID execution semantics, which means that it's atomic, which allows you to do very funky things. For example, you can give someone $1 billion and not worry about it. Because it's going to be atomic, it means that either the whole transaction completes or nothing completes. And so you can give them $1 billion, even though they didn't give you a dollar, because then you can control whether the transaction completes or not. So when the transaction completes and they use this $1 billion and they return to you more than $1 billion, then you can just take your cut, take the billion back and give them the dollar amount that they want, basically. And this is not hypothetical. You can actually execute right now code that will play around with $1 billion, and it's only going to cost you about $100, maybe less, which is, I mean, try going to a bank and ask for, $1 billion, and here's $100 I give you for it. So obviously, nobody's going to trust you with $1 billion. But here, nobody needs to trust you because it's ACID semantics. So either it completes or it doesn't complete, and I'm the ultimate arbiter whether it does complete or not, and I'm the one who gives you the money. So at the end of the transaction, I can either say, yes, it executed correctly and I'm happy, or I revert the transaction and everything reverts and everything rolls back, just like with an ACID database. Okay, EVM has its own EVM-specific programming language called Solidity, which has its own intermediate representation called Yule. And maybe this is not as exciting, but its consensus is not proof of work, but proof of stake. I'm not going to go into the detail. And there's soon something called data availability layer. So there's also, of course, the transactions that happen, which is called that's why it's called the blockchain, because all these blocks eventually create this chain. But now we have a new layer besides the consensus layer for the proof of stake. We also have the data availability layer for so-called roll-ups, which are secondary chains that allow you to execute transactions much faster and cheaper. The downsides of EVM is that it wasn't, so it's currently the code and data are not clearly separated. There is some change that will come that hopefully will fix this. And jump destinations can be dynamically computed, so that's kind of annoying because computing a CFG is kind of hard. And every instruction operates on 256-bit values, which probably should ring some bells, because that's a problem, right? If you're writing SMT solvers, then 256-bit semantics are going to be a big pain, because everything will blow up. So let's talk a little bit about symbolic execution. If you haven't heard this term, then maybe I can just do a little bit, I explain it, or if you have, then maybe I can do a bit of a refresher. So here's a bit of a pseudo assembly. Let's say that these are two registers. This is the register state when we start, and then we move register B to A, so now it becomes 2, and we add 4 to register A, and now it becomes 6. So this is the concrete execution semantics, right? So it's very easy to do symbolic execution in this sense. All we do is we replace all the things that are concrete with variables, so V1, V2. Now we do the mov based on the symbolic values that are in the register. So now it's the AX becomes V2 instead of V1, and then we add 4 to it, so it's V2 plus 4. It's quite easy, actually. So like, it should be quite easy to explain this to even someone who just started writing code, for example, so a junior engineer. Of course, the hard part is actually not this. The hard part is something else. The hard part is that once you have branching, things explode. Because here, the concrete execution is quite easy. We compare AX and BX and their equivalents, so we jump to this, and we say, okay, add 5 to AX, and now it's 6 and 1. So now we're happy. So this is the concrete execution. Symbolic execution is going to be a bit different, because what happens is that this comparison is operating now on a symbolic value, so now you can jump on 2 different places depending on where you actually went, and you might add 4 or 5 to V1 depending on where you jumped. So at the end of the execution, you will end up with 2 branches, basically, that you will now need to execute separately, symbolically. And of course, this is exponential, because if you have 100 branches, then it's 2 to the power, 100 jumps, then it's 2 to the power, conditional jumps, then it's 2 to the power of 100 different paths that you need to follow. So this is kind of the hard part. The easy part is actually all these things, which all you need to do, quote unquote, is make it all symbolic, right? So all your registers, instead of being concrete values, now are variables. Not such a big deal, actually. Okay, so what is HEVM? So HEVM is called HEVM because it's a Haskell EVM. It's written in Haskell, and it is a symbolic execution framework for the EVM virtual machine. It can do both concrete and symbolic execution, which is very handy because because we have a good concrete executor, of course, that everybody's executing to run the blockchain, and we can fuzz the system against it. So in case we have some discrepancies, we can find it and we can correct it. It takes as an input a negative or an invariant test or a suspected equivalent code. So it takes as an input either a negative test, an invariant test, or 2 pieces of code that you suspect to be equivalent and you hope that they are, and then see if you want to prove that they are indeed equivalent. Examines all execution paths from the starting state. Of course, all is in quotes here because of the explosion that I just talked about. We could try to improve that, and I will talk about that later. Finds a set of requirements to reach the failing state. So all the assertion violations that are potentially happening, it will find them all. And it can run an internal fuzzer or an external SMT solver to find these inputs to trigger these bad states or non-equivalent code or like failing invariants, and displays the actual code needed to trigger it. So you can just trigger it by hand, basically. Okay, so a very easy one. Here's a negative test. You have some tricky function, and you don't want this to happen. So if you get into this place, then bad things happen. The problem with this function is that it's full of magic numbers, and these magic numbers will be very difficult for a fuzzer to trigger. So a fuzzer will try all sorts of numbers in here, of course, to try to trigger this assert, and will fail. Symbolic execution will immediately figure this assert out, because what it will do is that we'll go into 2 different branches here. One of the branches clearly doesn't fail, so it doesn't even deal with it, and the other one it basically adds these 2 equations into the SMT solver, and the SMT solver will just spit out the solution, and that's it. So this is a sort of a typical example that people give for symbolic execution, but it's a negative test in the sense that we don't want this particular assert to happen. These kind of magic numbers, row, they don't, but sometimes they do appear in a tricky way. For example, overflow. So, or which is quite tricky to get right, is when you're, so EVM only deals with integers. So when you want to calculate percentage, for example, you're going to have to chop something off at the end, because you're going to multiply by 0.1, and it's not a value that, you know, can be represented in perfectly in an integer. And now what you chop off and how you chop it off makes a huge difference. There have been, like, people made, I don't want to say 100, I think probably tens of millions of dollars on these chop off things. So you can make a lot of money on this. And that's very tricky, because now you have to give just the right number to trigger the wrong chop off for you to gain that. You know, you don't need to gain much, because often you can just amplify it by doing it with a large amount of money. And, you know, because you can borrow $1 billion for $100, you know, if the chop off is bad, then you can really make a lot of money on it. So these numbers don't appear, but like these kind of edge cases come up quite often. It's very annoying to deal with. Yeah, and the fuzzer might never find it, because it's a 256-bit integer on top of that. So there's a large space. It's not like an 8-bit integer where, you know, fuzzer will have a good, or maybe even a 32-bit integer where you have like at least some kind of coverage. With a 256-bit integer, you just have zero coverage no matter what you do. So invariant checking is very similar. So you have a function that computes the invariant, returns the invariant whether it holds or not, and then the way you do it is in the function you put something called require, which is a keyword that doesn't actually trigger an assertion violation. You just say that this function never does anything if this invariant doesn't hold, and of course you assert the invariant at the end. So it's very easy to do this kind of invariant checking, more or less the same way that I just did the assert false, except that here it's not a pure false. It's a computation that you do. And then, of course, there is equivalence checking, which is sometimes useful because I haven't introduced this term gas, but gas is basically your execution costs. So of course, executing things on the network costs money, and this is represented by this gas. And sometimes what you want is there's a known good computation that is slow but does the job well, and everybody knows it does the job well. And then sometimes you can create more complicated but more efficient function that uses less gas or runs faster, which way you want to put it. But you're not sure if it's correct. So HEVM can also do this kind of equivalence checking and trigger the discrepancy. Okay, so this is what HEVM can do, and this is what symbolic execution is about, basically. And now I want to talk a little bit about the sort of the nitty-gritty of what HEVM is actually doing and how does it actually work. So first of all, it eats EVM bytecode, so it doesn't take in some higher level language like you would take C or C++ or Java or something like that. We actually take in the binary, like the pure binary, which means that we can run on everything, because of course anything that runs is always public because it's the blockchain. And we have a symbolic execution engine in there that generates the expression, this gigantic expression usually, that is kind of very mind-numbingly simple, in the sense that when you execute it, it just becomes larger and larger and larger, the way that I explained with, you know, v2 and then of course +2 +4 times 2 eventually. So it gets larger and larger and larger, and eventually you terminate, but it's a gigantic expression. So what you need to do with it is you need to do some kind of rewrite rules on top of this expression for it to be meaningful. And so the symbolic execution will do this kind of mind-numbingly simple, depth-first, full execution of all different branches that you can have. Then we have something called an array simplifier, which basically is doing simplification specifically for storage, which helps with, I mean, storage is one of the hardest parts of EVM because I'll explain in a bit more detail, but it's basically, they don't have structured memory or structured storage, neither structured memory, but nor structured storage, which means that storage is not, you can't cut it up into chunks. You will have to address it in a very weird way, which is what they do, and that makes it quite hard to simplify. And then we also have something called the catch-check constraint generator, and catch-check is the SHA-3 function, so it's the hash function that you might be aware of. It's quite often used to generate max message authentication codes, but in this particular case it's used as a sort of a magic compressor. So you put in some value and it compresses it into a 256-bit value. And this catch-check function comes up a lot in digital contracts, partially because of the storage, and you need to be able to deal with it. Unfortunately, catch-check is gigantic. It's a huge hash function that is very complicated, so we will not precisely model it. Instead, we will try to model it as best as we can as an uninterpreted function, and I'll talk about that in a moment. And then, of course, we have to generate the SMT expressions, or fuzzing, and out of that, we have to eat the output of the SMT, get a counterexample, and eventually generate a function call for the user, so they actually Yeah, good question. So the way we know it's a bad state is because it's a convention that the call that, so there's a return data that is returned back to the caller, and that return data is in a specific format. And if that format, you can actually exclude or include different types of errors. There are different types of errors that are just conventionally agreed to be, bad or good or whatever. And then if it's just a revert, like a require will just simply revert, which means that there is no, it still, of course, returns an error, but it's like it's a conventionally agreed one that, is not a error state. It's just, we're just gonna revert and that's it. Of course, like you can decide, it's up to the user to decide, and you can actually you can modify it on the command line of what you want to be an error, like what is wrong, basically. But assert is a good way of doing it, but there are other ways of reverting that are not very good. For example, if you run out of gas, so if you run out of the execution, the money that you gave for the system to execute your program, eventually it runs out of this money, and then it just reverts everything because, well, I can't execute anymore and I don't know what the output is, so I'm just going to revert everything. So that's one way of reverting. It's not a very nice way, but it will also revert, and it will also give you an error code. Yeah, but it's a good question, right? So the bytecode itself encodes what is wrong, yes, through these conventions. Right. So the symbolic execution is, just to start with the HEVM's symbolic execution, it operates on bytecode, as I explained, understands all of EVM. So there are some so-called symbolic execution frameworks out there that do some of it, or partially, or understand some parts and don't understand other parts. The HEVM one actually understands everything from stack, call frames, memory, storage, call data, return data, everything. Which means that you can actually set it up to run from any point in time, from a year ago, 2 years ago. So you can simulate any kind of execution from any time, symbolically or not, of course, because it's also a concrete executor. And you can chain any number of symbolic transactions after each other, which of course is not very difficult. Once everything is symbolic, all you do is you execute this transaction and you take that state as the starting state of the next one and you execute it forward, right? That's what you do with the instructions as well, but here you can just do it for the whole transaction. And it's you can actually fuzz the symbolic execution against the concrete execution semantics of the Go Ethereum client. Limitations, well, yes, there are some. One of them is that it cannot deal with symbolic gas. So gas is quite an annoying problem, and most people ignore it. But again, gas is the money you give for people to execute your contract, and eventually it can run out. And some of this execution is non-trivial. For example, exponentiation doesn't have a fixed gas cost. It actually has a gas cost that is dynamic. And now your gas itself, so it's almost like a PC, like a program counter, but not a program counter, but itself becomes symbolic, and that's just a bit too much, so we don't do that. And there's this is a bit more serious, and we should work on it. Is symbolic offset and size memory copy is not yet implemented. So if the offset or the size that you're copying from memory is symbolic, then we just give up, which is quite rare actually in digital contracts, because this would allow an attacker potentially to just explode your contract, because you give it some large number and it will never execute, or so it can be kind of a problem. And Yeah, because it runs on the bytecode, it doesn't actually understand any higher level constructs. So you need to recover all the higher level constructs, just like you do with SAT solvers. Actually, in that sense, I was kind of close to this, because in SAT solvers everything is always blasted to hell, so everything is blasted to booleans. All you have is zeros and ones. So recovering structure from that is also quite painstaking sort of process, but it's very useful when you do it. And so it's very similar here. You have this effectively set of assembly instructions, and now you figure out what is the CFG, the control flow graph, for example. Okay, so the real kicker, I would say, in HEVM is the intermediate representation, which is going to be the rest of this talk. I hope you won't get bored. It's basically the core of the system, because what happens is that the intermediate representation is the expression that we generate when we're symbolically executing. And this kind of symbolic execution is kind of very dumb in some ways, and eventually you'll have to do all the smarts once you have done the heavy lifting. But let's go from the top down. So here's a very simple function. We're checking whether, I know that this can overflow, so I'm going to say b is equal to a plus 1, and I say that b must be larger than 1, larger than a, which, it would hold, but unfortunately this overflows, of course. And once this overflows, then this will become, b will become 0, and a will be a really large number, and then this will no longer hold. And we would like to generate the expression like this. So a proposition that less or equal, this thing is less than or equal than this. So the addition of variable 1 plus a plus 1 is less or equal than a, right? So that's a very clean sort of expression that you would like this to have to generate. But instead what we do is something very simple at the very beginning, at least. So we start with, let's say, if you're writing on top of a storage, then it's an abstract buffer, with variable number a, and then we're gonna write a word on top of it, which is going to be the constant 1 at position, the variable a at position 1. And then we're going to write variable b at position 2. So it's just a write on top of a write on top of a write. And that's exactly how it's going to be if you add or multiply or anything like that. So all that's happening is like we're moving this thing here, and we say what we're going to do on top of it. So here we're going to write a word to position 1, and that word is going to be whatever is in variable a. And then we're going to shift this whole thing here, and we're going to say we're going to write variable b at position 2 on that thing. So this allows you to very simply generate the formula when you're doing the symbolic execution. Because remember that the symbolic execution itself is quite complicated, because you have to keep in mind all the semantics of the virtual machine, and you don't want to deal with that when you're building your. You want to deal with that only when you're building your expression. And then later you're going to simplify this down, or hopefully you will simplify this down. But at the beginning you make this very complicated, very verbose kind of expression. So this is the intermediate representation that we do. By the way, this has some negative aspects. For example, what do you do here exactly when it's like a symbolic, like a copy that is starting from a symbolic position with a symbolic size? While the overwrite is not going to be very obvious, like what is actually going to happen. There are some ways of doing this with interval graphs and whatnot, but I'm not going to go into that. We don't do it. So in case of symbolic size and offset, we'll just give up. Okay, so the catch-up part. So SHA-3 is this is a hash function that is quite complicated, and it is used extensively in contracts in the Ethereum or ecosystem. Partially because storage of contracts is unstructured array. I'll talk about this in the next slide, but it's kind of the two depend on each other, so I'll explain that later. But basically this catch-up is extremely important and it's used everywhere, but we can't represent it in SMT exactly, or we could, but it will never terminate running anything. So we have to do something else. And the way we do it, and the way most people do it, is using a form of uninterpreted function in SMT, and then we add some we add some things that will constrain this uninterpreted function. For example, if we know what is the input, then of course we can just assert that the catch-up of this input is going to be that output. It's quite easy. We do this for all the constants in the expression. Size value of the hash differs. So if you hash a different size thing, then they will be different. So we add all the pairs that are catch-ucked with different size to be non-equivalent if their size is not equivalent, because the size will almost always make it with an extremely high probability they will be not equivalent. We assert all pairs unequal if any of the concrete values that are partially known about them, because we might not know all the parts of the input, but we might know, for example, the first 2 bytes of the input, and if they're different on that, then the output will be different, therefore the catch-up will be different, so we assert that as well. And we also assert some very obvious things. Sorry. Oh, was there a question?
No. There was a technical glitch in the online thing.
Oh no! Yes, I will rejoin it. Oh no! Oh, meeting has ended.
It just terminated.
Oh, okay. Let me see if I can do this again. I don't think I need, hopefully. So this Jabra speak. Yeah, that sounds good. I join meeting, and then I should start. Oops. Ooh. That's not good. Uh-oh. I'm not making this any better. Oops, no. Oh no. Okay, now that should do the trick. I think that should do the trick. Yes. Ooh, oh no, what's going on? I don't know how to deal with this. Oh no. Okay, I'm stopping this one, and maybe this needs to go back on. Okay, I think we're now good. Yeah, I think we might be good now. No, I want to start the video and I want to share my screen. I think screen 1 will do the trick. And now we can go back to, hopefully, this thing. Yeah. Does this work now? Oh, that's good. Yeah, sorry for the short interruption. Okay, so we basically assert a bunch of things about this uninterpreted function, because otherwise, of course, it's uninterpreted, so it will just, and the SMT solver will just make stuff up, which is nonsense, and we don't want that. So we need to be able to constrain it to some sane thing, and for example, the catch-up value is never very small is a good idea, because there are some particular things that we'll need later that will help us if catch-up is never small. And it never is small, because like, if I could figure out what is the value that hashes to 0, then somebody would give me some good money, I'm sure. So it's quite hard to reverse these kind of systems. That's how they're built. So maps, right. So this is the problem with, yes?
Why do you make the phone?
Because of arrays, actually, which I'll talk about in a second. So because the catch-up is then used later in this way, which is to say, okay, so the problem is that the storage of this contract is actually not structured, and because it's not structured, all you have is just imagine it as a giant array where you can index into, and the index is a 256-bit value, and you can write anywhere, and it will only cost you as much as you know. If you write there, then you pay 1. If you write another place, then you pay 2, etc. So you only pay 1 each. So you can, it's a random access memory, like storage in that sense. But the thing is that, let's say that you have 2, like this would work with 1, but let's say, I have 2 mappings. Like, what do I do now? Because I can't just like take this uint and, and map it to that uint, because they'll clash. If I put, the value 1 in here and then I put the value 1 in there, then, they'll map to the same place, and now we're gonna clash. And the way they resolve this is by catch-a-king the ID of the map. So the ID starts at 0. So this will be a 0. And the key, let's say, is 1. So what will happen is that if I want to put 1 in here and 1 in here, then this will be a 1, this will be a 0, and this will be a 1, this will be a 1, and they're Ketchuk. Both of them are Ketchuk together. And now this Ketchuk will almost never clash. Like, that's the idea, that it will never clash. And the array is very similar. You basically put a fixed value in here and the ID of the array, and then you index into that +1, +1, +1, +2, +3, +4, etc. So from there on, the array is linear, but it starts at basically a random position. And this helps it not clash with another array or another map, hopefully. Of course, there's always a chance of it clashing, but if you can compute a clash, then you can make more money, so it doesn't matter.
Where are you using the part that is large?
Yeah, that is a good. It's still not here. What happens is that that's a double Ketchuk, and one of the Ketchuks is inside the other Ketchuk, and that, if that's small, then it never clashes. So it's a sort of a, which makes Ketchuk even worse if you think about it, because now we really need to be able to like very accurately think about Ketchuk while not being able to accurately represent it in SMT. So these things really need to be quite powerful. We are actually thinking about even more, and you can add more constraints on this uninterpreted function to have a more accurate representation of what Ketchuk is, and then you will have much better results at the end. But it might take you more time to do it. So some people, what they do is they do this, and if it's correct, then it's correct. They output it to the user. If it's not correct, then they refine it. So this would be a form of abstraction refinement, where you almost like a CGAR kind of thing, if anybody knows what. So this is the counterexample guided abstraction refinement, where you basically do a sort of a dummy way of doing this. Let's say you only put like 2 of these in, and then if it gives you a spurious counterexample, then you refine it and add more axioms about this uninterpreted function, so you get a more precise solution at the end. Hopefully an ansat, in case it really is ansat. Okay, so I'm just going to go very quickly about this. This is the set of simplifications that we do. This is not even half of it. I don't think it's even 10% of it. So we do some kind of canonicalization of the expression, of course, because that allows us to make sure that, for example, all the concrete values are first, so we can compare subtrees quite easily if they're the same. Because like if there's an equivalence, like this thing is equal to this thing, and the two are actually equivalent, it's just that you need to, oh no.
The online can't hear it.
Oh no, that's really bad. I'm really sorry. I don't know how to do this now. Wait, what? Oh yes, that's correct. Here. Okay. How about now? That's maybe
Here? Now?
now. Maybe I was muted. Hello. Woohoo. Let's see. Divesh is talking, but I can't hear them. Oh yeah, because I took the sound down. Okay, now talk. Let's see. Can you talk? Divesh?
Yeah, I can hear you.
Oh, that's perfect. Okay, now everything works. I'm really sorry. Okay, let's hope this will now keep working. Yes, because it was working when we set it up, but then, yeah, the technology failed us. So there's the canonicalization, right? So that just to make sure that in case like I assert 2 parts are equivalent, and they are really equivalent, it's just that they're like, for example, it's a commutative operator, and you can flip it either way. Then we want to flip it in a very specific way so that we can syntactically compare the two to be semantically equivalent. Same thing for less than, greater than. Of course, you can just swap around the left than, less than, greater than. So I just make everything less than. It doesn't matter. You can also make it everything greater than. We don't want 2 operators. 1 operator is good enough. We also canonize all Ketchuk expressions to match these kind of patterns that I've shown. We then strip writes that are not read and strip reads that are not used. We do constant folding, obviously. I mean, that's quite an obvious one. We do actually, this is quite fun, this equality propagation or inequality propagation. So if we know that A is equal to B, then we can replace everywhere A, like everywhere B is, we can replace with A, and then we can, of course, again do kind of simplifications, etc. So we can do this all to fixed point, of course. And then, I mean, this is just a very small subset. I can give you some fun examples of how long this code is. But effectively, at one point, you start writing an SMT solver, because these are just like, oh, it's too small, but maybe the next slide gives you a sort of a, yeah, here's the next slide. So here, like this is just a rewrite of like if both are constants and we assert that them to be the same, then if A and B are the same, then it's a 1, otherwise it's a 0. Or if equivalent A or B, and we don't know what A and B is, so this is an algebraic data type, so this can be anything. This can be in a gigantic tree, both A and B. Then we can just check syntactically if they're the same, and we don't even need to compute what it is. And if it is, then it's just the 1, and that's it. So this is Haskell really helps us a lot here with these algebraic data types, and also with pattern matching. So this actually pattern matches on A and B, whatever A and B is. They can be another structure, and it doesn't matter. It will correctly understand that. So it's quite, Haskell was not a bad choice in this sense, because it can really help us write these kind of rewrite rules quite simply. So this is the kind of rewrite rules that you see. Like, I don't know, this is about mod, but there are other ones about less than being rewritten to greater than being rewritten to less than, I'm sure, somewhere. So there's quite a lot of here's some buffer simplification, storage simplification about Ketchuk, of course, etc. Okay, I think we're gonna run out of time, so I just want to make sure we get to the next slide and eventually finish. So this IR, let's say that we did generate this IR and we simplified this IR all the way. So what can we use this IR for? Obviously, one thing we can use it for is create an SMT query. That was sort of the original idea that we wanted to do, of course. Oops, I think I'm creating noise. Is to generate SMT queries, but we can do other things. We can also, for example, extract constants. So remember those constants that were in that fuzzer part, and it was kind of like, well, maybe somebody could be smart enough to extract them. And actually, you can do that. And these are called these kind of magic numbers that can help a fuzzer sort of break through. And you can just extract them and put them in a fuzzer, like in a professional fuzzer, like a fuzzer that is made for this kind of systems. But
extraction using rewrite rules?
Yeah, you can. I mean, actually, the way that I do the extraction, I actually have this code. I can show it to you. It just walks recursively the tree and finds any literal, like lit x, where x is a concrete value in this case. It will just extract it and put it in an array, and then use that as a fuzz input. And I actually did this. So I now do this. We actually have a fuzzer inside HEVM which extracts these constraints and just like tries to substitute and see if it works. And if you don't actually deal only with failing branches, which is the question of CoolDeep, like you don't want to only think about like what fails, but everything, then you can actually just create automated test case generation, because of course all these, so the symbolic execution finishes, right? And you have all these different potential branches. Now with an SMT solver, you can query if they are any reachable at all, right? You prune all the ones that are not reachable, all the rest are reachable. So I can just, they are all test cases. So now you can maybe run a Maxat solver to find a minimal test case, like a minimal value, because like if you give some like large number to the test people, they will be like, what is this number? Why is it so special? If you run a Maxat solver, you will get something like 0, 1, 2, these kind of things. So it will be much more meaningful to the engineer, like, oh, this is what this test case is doing, and they might be kind of surprised about some of the test cases that can actually go through, and then you can like, ooh, I didn't want that. So that's kind of nice. Okay, so a fuzzer, I've been working on this, so I'm a little, it's close to my heart. The more interesting part about this fuzzer thing is that since you generated this IR, so this generated this expression that's quite compact and describes this one particular behavior of the system, you can actually extract this expression and create an assembly code that runs nothing but this expression. And then you can run it really fast. So you can, in a sense, it's like a targeted fuzzer that specifically writes a code that runs only that one path. So we can basically take this expression, write a C code that is like a very dumb auto-generated C code, then run a compiler on that, get an assembly output, and the input of this assembly would be concrete values, but now it runs assembly. It's not running this weird 256-bit machine with all these weird behaviors that is very complex to run. And so the original, this Go execution, Ethereum execution framework is incredibly slow, like really, really, really slow. So we could do much better, actually. So that's kind of a cool idea, and we already have some of this, but not the transpiled, so it doesn't run an assembly. Just, of course, substitutes the constants and constant faults. I mean,
So this could be done for any symbolic symbol.
yeah, it could be. Yeah, it really could be. No, I'm serious. It could be. I think it could be very fun, actually. No, I'm not sure it has been done, but I think it's very cool. Like this not, I mean, I think this transpilation into assembly, like of intermediate representation, of course, is not a new thing because like this is what compilers do, right? But it's kind of I think it's not a completely idiotic idea.
Far more deputy rewriting than
Yeah. I mean, yes. So I think this could be quite cool, especially in the in the world of EVM, because EVM execution is just so slow. So here you could get much faster execution, like much faster. I don't know how much, but I mean 100 would be even not that much. I think like 1,000 would be a more like I would expect that level of speed up. Anyway, so the SMT of course is very simple. So this was the last expression. Remember that, you know, like we add 1 to A and now it needs to be less or equal to A. This is the SMT expression that gets generated. I mean, it's the simplest thing you can come up with, basically. You define a sort called word that is 256-bit long. You generate A is a word, you declare this constant, and then you do the BV add, you know, and assert that it's unsigned less than equal to, and assert and check SOT. So it's really the basic thing that would come out of something like that. And eventually Z3 gives you the thing that you were looking for, the FFFFFF, you know, that's just about to roll around, right? So it's not like, you know, magic or anything. And okay, so this is just how you can run it. It's not a big deal. You write, like, it's literally that. Like, that's how easy it is. The only thing is that you have to put prove in front of your function. And then it will check all the asserts. So that's just to sort of set up the stage for the next slide, which is our results, which are not amazing, but they're not terrible. And on top of that, they're we like this is not the best test set. We need to work on benchmarks. That's one of the problems actually in this space. The benchmarks are not very good. So the purple one is actually Halmosh, which is written by another team that are very, very good. And the green one is us. And this is the time. And these are the different examples that we have. As you can see, there's not too many benchmarks. That's actually really the problem. We're most of the time slower than Halmosh. But to be fair, I think the problem here is that these are not very complicated benchmarks. The rewrite rules and all the simplification systems, they really pay off for complicated stuff. For simple stuff, you just pay the overhead and you get nothing. So I think that's the reason why we're sort of sometimes slower. Sometimes we time out, but it's not really. So here there are some things that are different between. This is also a problem of what do you mean by finishing a problem, like solving a problem, because Halmosh, for example, exits the first time it finds a counterexample, and we don't exit until we have found all counterexamples, and that's a big difference. So. Yeah, they also do a lot of rewriting. Yeah, they also do a lot of rewriting. We also do actually abstraction refinement. I didn't go into all these details, but you can, for example, do abstraction, and I stripped away from here the abstraction refinement, but you can actually do abstraction refinement with the storage. So you can say all storage reads are a new variable, right? Quite simple, like all the storage reads are now gone, basically, because they're just a new variable. Of course, they're not, some of these variables are the same variables, but you don't, that's like sort of hidden to the SMT solver. And you can sometimes still prove unsatisfiability. So no matter what is in the storage, it's still unsatisfiable. And that, of course, simplifies away a lot of the catch-up and all these kind of things are just gone. So you can do quite a lot of kind of cool things in this space in terms of abstraction refinement at the IR level. Because remember that the SMT solver itself does abstraction refinement at the SMT level, but now you can understand sort of more deeply what's going on, and you can do abstraction refinement at a higher level than the SMT solver would do. So we actually do that. We have a number of configurations. I just stripped away from this graph, but we do have this kind of abstraction refinement. Oh yeah, this is the time, and these are the different instances, and like these two correspond to one instance, of course. So the Halmosh seems to be always faster. I think it's maybe always faster. I think it's maybe always faster, but it's not a good. That's not. Yes, well that, and also there are some some things where I think they output like where we're sort of unsure, but we're gonna say on that. So that I mean, it's not really. I understand them to some extent because it's especially with Ketchuk, it can be kind of complicated, and this has been the trend for a while anyway. When it comes to this kind of symbolic execution frameworks, or originally they were used. So just so everybody gets. So that's why there's only 2 here, which is kind of strange. We've been in this industry for 7 years. Like, what's going on? So what's going on is that a lot of these systems were built as static code analysis frameworks. And then they use symbolic execution only to filter out the obviously wrong static analysis like results. So the symbolic execution was used as a sort of a filter rather than as a like this is what we do kind of thing. So the symbolic execution framework part was always an afterthought and was never precise, never really precise, because they didn't need to be really precise. And that's the reason why we're sort of here. This K framework is missing from here. They are the sort of the OG people who have done this for a long time. If you know something called Uniswap was checked with K framework, but it was a lot of manual work, But it does actually do it. It's just, it needs like a terabyte of memory. I'm not kidding. Like, it needs something like a terabyte. So you can get that. So it's not like the end of the world. Like, if it's only a terabyte of memory, that's all you need. That's actually not so bad. Like, you know, because you can run that machine for like, you know, $100 an hour. You run it for 2 hours and you're done. You know, like, no, you know, not the best thing ever, but it works. You know, but yeah, that's So the K requires. It's sort of a little old, but very good. So. Has its own advantages. Also a gigantic rewrite system. The K framework is nothing but a rewrite system. Okay, so limitations and future work, just a little bit to wrap it up. We have issues with loops. Of course, now we do these loop iterations to a certain level, but I would like to work with maybe Supratik and Kuldeep on invariant synthesis. I think that could be quite nice. Maybe we could use some kind of functional synthesis work that we've been, they have been working on, and I've been reading. So that could be kind of nice, I think. Recursion, parametric calls, we can only partially explore. Recursion we can still do invariant computation, so that could still be very useful. Complicated mathematical expressions, we can't do anything with that anyway, like division, modulo, things like that. Maybe there is actually abstraction refinement you can do at this level as well. We're also doing that, but it's kind of it's unclear if it's really working. And HEVM itself, of course, is not verified. So you get some kind of output and you hope that the code that we have written is correct, right? We do some kind of fuzzing. The SMT solvers can sometimes, some of them will eventually be able to output some proof that you can verify, but you know, that there's still like this intermediate step that is not verified. We could actually try to do some kind of cock proofs for some of the rewrite rules. That would not be insane, but you still now have to verify the symbolic execution system and the translation to SMT. So anyway, future work, some CFG, so some control flow graph, invariant computation I mentioned, some SMT solver tricks we could do. I mean, this sounds small, but it's kind of useful in the graphs. It's not that exciting in terms of like research, but it's useful. And I mean, this is it's kind of funny because now we're going to the static analysis from the symbolic execution side, which is basically just add some invariants that should always be there, even if the user didn't add them, and then notify the user in case they are violated. So this is kind of pre-written rule set almost. Okay, so that's it really. So HEVM is this kind of, well, we hope to be a future fully featured EVM symbolic execution framework that is kind of easy to use. And I mean, this is what it takes to actually write it, like to write the code. So it's actually really, really simple to set it up and use. It's not, you know, doesn't require like a complicated setup. Yeah. So that's it. Yeah.
Questions?
Can HEVM detect re-entry attacks?
Good question. You can set it up to do it. So that's kind of the way to put it, but so I think we need to work a little bit more on this kind of like basic, this kind of invariance that I was talking about. so that it would detect it automatically in a sense. Can it detect it? Yes, because it can do multiple transactions. So it can simulate the whole EVM, like symbolically. So it can, but the thing is that it's not like sort of there's no particular like line in there to do it. And I think that's kind of this usability issue from my perspective. Like as a developer, I see it as a usability issue that we should support this more easily for the user to do it. But no, currently, yeah, I could write it, but you could probably write the assert, but it might be complicated to set up HEVM to actually really do that. Yeah, but it's not impossible to do it because it's a functional programming language. It's quite easy to express these, things like reentrancy or like chaining things together. It's just super simple with HEVM because of the functional programming language that it's built on. But yeah, you're right. That's usability is next year. Like that's literally what we're going to be working on next year to make these kind of things like just more accessible. But yes, that's a classical issue. Yeah. Good question, actually.
No, I'm going back to this small values. I was thinking that if you know that, because the previous assumption said that the two hash values are not equal.
Yeah.
If they are not equal, then it would imply that even if you take the catch-up again of the...
I think what happens is that it allows us to completely, it allows us to, so what happens... Okay, so that lets us get a little deeper, but it's still good. So what happens is that it's going to be a chain of writes like this. Remember this chain here? This chain? So it's going to be like an empty concrete buff here. It's going to be an empty concrete buff because it's an empty buffer that you're writing. And there's going to be a chain of writes on top of it. And what you want to do is eliminate every part of the chain except that the one thing that you're reading. And then, the rewrite will be like, oh, this is exactly what we're reading, and there's nothing else in this thing, so we can just this is the value, and you just take out the value, and that's it. So basically, you want to collapse this, read, write. That's what you want to collapse into like a single value, right? The one thing that was written. And it helps if this, I'll have to get back to the code to be honest, but if I remember correctly, it helps with this because the arrays indices usually tend to be small, and one of these, if you do an array write, like on top of, after another, then it helps with eliminating some of, parts of this chain. But I'm a bit vague on purpose because I would need to read the code. But it's a chain of writes basically, and what's annoying is that this read is very clearly like this write is the one that it corresponds to. But of course you need to make sure that nothing in between is overwriting any of that, right? So that's very important because just because this one is clearly what is being read here. It could be that something in the middle have overwritten it, right? Because this is the value at this point, and then there's something writes on top of it, something writes on top of it, and now you're reading it. And what you need to make sure is that these two that have written it on it are not overwriting the value that you're trying to read. And you need to be sure about that. And the only way to make sure to be sure is, for example, those in the concrete values they are different. So you can say, oh well, Ketchuk will never hash to the same value, so we can just ignore it and take it out.
That's why I'm asking why. Because you could say that if it's any array indices, if you know their range and the catcher, because we know that you can't invert it, so it kind of.
I wonder what's going on. I'll think about. I'll check it for you. But it's a good question. I remember that it was helping for a specific case. I mean, I was looking at normally I'm looking at the IR. So this is what I'm usually staring at, in case you're interested. This is the sort of the unsimplified IR, and here what it's doing, for example, is that it's checking that no money has been sent. Like this TX value is the money that has been sent with the transaction, that is 0, and the buffer length of the call data, so the call data that we're being called with, is less than 4. And in that case, we're going to fail because the first 4 bytes are the function selector. So we select the function that we're going to call with the first 4 bytes. And if the thing that we're, the call data is less than 4 bytes, then this is just going to revert because it says, well, you're calling a non-existent function. Every function has a 4-byte, descriptor, so that's not gonna fly. And then we're gonna, this is gonna be this I think is the Yeah, this I think, or one of these parts is going to be the function selector itself. Like here, for example, this is this will give you a call data that will kick this function. It's quite simple to see this. We actually call this thing with a bytecode. So this is the bytecode. Like literally, we're calling it with the assembly in a sense. Like this is not structured in any way, and we got this value out by just running the compiler on this structured code, of course. And this was the roll around query. Or it's the roll around query. Yeah. So you run it, we get this this is the bytecode, and then we just like put this bytecode in there and da-da-da-da. And it also gives me we'll need to fix this. This is the unsimplified version. That's why it's kind of annoying, but to read the simplification. But this is actually, for example, the error. So this is when it's an error. So this is how you know that you were asking why do you know this is an error? Well, that's how I know. So this is this agreed upon value that we return in the call data in the return data that we know that it is wrong. So this is an error. It also says error, but yeah, instead of just a revert. Anyway, so that's but yeah, you're right. I'll check it. We need to check it. You're right. Good to push on it. But yeah, so the idea is that you want these chains to be, the middle of the chain to be short. Of course, you don't care what's after that, because whatever was there, you have already overwritten it. So you can strip that. The problem is you can't strip it like in between. You need to be sure that you haven't overwritten the value that now we're reading. Yeah, I don't know. I think
Choice of Haskell.
It wasn't mine. It was somebody who did it many years ago. It's a blessing and a curse. Sometimes I find myself very happy about these kind of rewrite rules being so easy to write, because it's like made to do this in some sense. Like these rewrite rules and compilers are incredibly easy to write in Haskell. And this, in some sense, this is a compiler. Like it takes in EVM bytecode and spits out an IR. I mean, eventually we translate to an SMT, but it's almost like a side effect, So it is a compiler, and writing HEVM like compilers in Haskell is very easy. But yes, the question is correct. Sometimes I wish it wasn't Haskell, because it has some disadvantages, but it also has some it does structural hashing actually of the tree that is being generated. So if you have this massive tree with subparts that are exactly the same, because it's remember this kind of overrides. So this thing is just going to be a pointer here, and it's just going to point to that pointer, and that's it. So it's just one more pointer that's put at the end, because this is going to be a pointer, that's going to be a point, like this is going to be a pointer here, and that's going to be a pointer there, and so this is actually only 3 pointers plus a little bit of data, which is not the same in like if you accidentally do this by hand in C, C++, it will not be that. And it does this kind of structural hashing automatically, so you don't have to do anything about it.
Okay, are there any questions from the...
Oh, maybe online?
Okay.
No.
That is
Oh, yes. Oh, wait.
Oh, there is.
Go on. Sorry. Yes.
Have you done any study where only the rewrite rules were sufficient to prove the given assumption?
Oh yeah, sure. That's all I do nowadays. That's all I do. I'm serious. I'm not getting rid of the SMT solver, but I'm trying my very best to get rid of it. That's the reason why I wrote the equivalence substitution and inequality checking and things, because that's kind of a mini. It's not a SAT solver in the sense that it doesn't do backtracking, right? The proper search system will do backtracking, right? That's kind of the idea of search. But the thing is that in case you can solve it without backtracking, then it would be nice if it could solve it without backtracking. And I've been putting more and more efforts into like doing effectively a form of solving that without backtracking. I'm not going to backtrack because that's a whole nother can of worms. But if you basically there is a mini solver in it that does these kind of checks. For example, if A is set to 5 and in different place, A is asserted to be less than 5, then it will say, hey, this is not possible. These are contradictory requirements, and it will just fall into false, and it will never call the SMT solver. It will just say, well, it's false. Which is also kind of tricky, because if you eventually, say, oh, we are verified because the SMT solver output a proof, well, there's no, I never even called the SMT solver. So clearly there was so then you really have to be careful about the rewrite system that you're writing, because, it will just, fold into unsat on its own. But yeah, the question is really good, and I would love to do more work on it, but not in a sense of a backtracking search. Like a forward search I'm happy with. Backtracking search I don't want to do, because then I'm just creating a SAT solver over the IR effectively, which is not completely insane to do either, but I'm not going to do it. Yeah, did this answer the question?
Yeah, sure, it certainly answers the question. So in some ways the sequence of rules that you apply, that itself becomes a proof.
Yes, and the sequence of rules that I apply, I sort of put a little note in I don't know if you saw it, I was a bit tricky. There is one place where this sequence is actually not obvious which way to do it. So there it is, at the very bottom of this slide, it says delayed simplification of Kerchak expressions to keep structure as much as possible. So actually, the rewrite rules is not always a good idea to apply them eagerly all the way. Sometimes you want to keep some amount of structure, or apply them in a specific order, because the order in which you apply them, of course, matters. And sometimes they're confluent. It doesn't matter which way which order you apply them, they're all going to end up at the same place. So that's called confluence. But often they're not confluent. And I mean, in SAT solving, it's very often not confluent. Also not in, for example, functional synthesis. It does make a big difference in which order you synthesize the outputs, right? A huge difference. And so in this case as well, it makes a big difference in which order you do it, and some of them are confluent, like constant folding is confluent, but some things are not, and you have to be kind of careful. And actually, we have bumped into the first major hurdle with that, and I spent quite a lot of time getting this delayed simplification of Kerchak expressions right, because you shouldn't apply certain simplification rules to Kerchak at one point. Or only apply them at the very end, otherwise you risk destroying a structure that allows you to do this kind of chain of right collapsing. I don't know if that...
I have two more questions.
Oh, okay.
I'll ask them, you get. So one is, this, I believe the catch expressions are your primary data structure. How are they different from e-graphs? And
yeah, well, yes. Yes.
Yes.
We should be doing e-graphs, absolutely. So if anybody's on, so there's something called equality saturation, which I think is what you're talking about, where you basically try to find the most optimal representation, given, of course, a different order of ways you can do things, and then you can sort of use a MUX-SAT solver to figure out, or MUX SMT solver, which set of rewrites will give you the best, most optimal representation. And there's this e-graphs is one way of calculating this in a fast way, and there's something called EGG, which is e-graphs done good. It's sort of this paper that everybody's citing now, and it's actually really good, very interesting. And we have thought about doing that. I even wrote an email about that to someone quite well known in the SAT world, because it could be quite interesting to do this kind of e-graph stuff. So e-graphs basically help you represent every single possible rewrite you could do, and then within this every possible rewrite, because all of these are equivalent, right? They're all equivalent. They're just a rewrite. I'm just adding a rewrite to it. It's all equivalent. So this is a gigantic equivalence class, and now within this equivalence class you want to find the element that is the smallest, right? That is the best, the most optimal rewrite that you can do. And that is, so these e-graphs help you find this one element. That's the idea. Did I summarize it correctly, or did I answer it correctly?
I think you summarized it correctly, but I believe you are saying that this is very close to whatever e-graphs.
No, we're doing, what we're doing is just not good enough. We need to do better. But we haven't done e-graphs, no. We should, you're right. That's the right thing to do. I just haven't yet, got there. But I want to do that. I want to do that with SAT solving. I also want to do that with this, but it takes time. But yes, you're right. We should be working on this, yeah.
The second question that I asked was, if invariants are supplied, I think now I can add on to that question. Do you have rules where if invariants are present, those rewrite rules can take advantage of that invariant to simplify the underlying model?
So no, but in some way yes. So if you put a require at the beginning of the function, then that will be an exerted constraint over the whole execution, of course, and that can help you simplify the rest of the formula. So in that sense, and if you put a require invariant at the beginning of your function, then because there is an asserted truth for the whole formula, some of the rewrite rules we use that assertion to simplify other parts of the expression. So we do this kind of thing where if you have an assertion, because basically this is kind of like asserting a truth, this require, like you know that when you enter this function you have this invariant, and that can help you simplify, you know, all the things that are happening in the function. Yeah, so that we do that. Yes, we do that, but we need more rewrite rules. But yes, that's correct. So we definitely do that. So if you put a require at the beginning, like a is equal to 1, then and use a, then later, you know, we will replace a with 1 everywhere, because we know like that was the invariant that a must always be 1 in this function. I don't know if that was answering your question, but I hope it. So there is a way of doing that with this require, and that will assert the fact, and we will use that fact to simplify things. Oh no. Well, I think we might need to end it here because it's like going on for too long anyway. Sorry for keeping you up all. Thanks for your time.